All right, now you're asked to find the equation of the tangent line to the graph at the given point. So what we were doing earlier when we had specific points given to us, we were just finding the slope of the tangent line. Now we are going to go a step further. So we're going to do the same thing we've been doing, but just add a little bit to what we're doing because we need the actual equation of the tangent line. All right, so first of all, let's start with our limit definition to find our derivative. So f prime of x would be equal to the limit as delta x approaches 0. Okay, so first of all, I need to substitute in the x plus delta x. So I would have 2 times x plus delta x squared plus 5. And then I need to subtract from that the function. And then that's all divided by delta x. Okay, now doing my simplifying. Okay, you would need to write this down twice and pull it out. You have to do that before you can distribute your 2. Okay, so now let's work on distributing our 2. Okay, now these two will combine together, which will give you a 2x delta x, but then times 2, so I'll have a 4x delta x plus 2 times the delta x squared minus 2x squared minus 5. I just realized something right back up here. After I wrote this down twice and folded it out, I forgot to bring down this plus 5. So don't erase what you have, just squeeze it in because it's actually going to end up adding out. So I have a plus 5 there. Let me squeeze in a plus 5 here. Okay, so you have 2x squares that will cancel, and as I said, the 5s are going to cancel. That's why I said just squeeze it in there somewhere. Okay, now the terms that I have left on the top, which are these two, have a delta x in common. So I'm going to bring that out front. So I'm left with 4x plus 2 delta x. So then the delta x's are going to cancel. And let's go ahead and do the direct substitution. So you're going to substitute 0 in for delta x. So you would actually just end up with 4x plus 2 times 0, which is just 4x. So this is going to be the expression that's going to represent your slope. And then you can use that, as I said earlier, to find the slope at any point that's on this function. So we're specifically looking at the point -1,7. Okay, so finding my slope first. Of course, my x value of this point's -1. So that would be 4 times -1, of course, which is -4. Okay, but now remember you're asked this time to find the slope of, or the equation of the tangent line. Now we're dealing with lines, and if you're asked to find the equation, you have to use, remember what's called your point slope form. Okay, so I've just found my slope, that's my -4, and then the given point, the -1,7, is what I'll substitute here. Of course, this will end up being +1 because it's minus a negative. And last, getting y by itself, you would have a +3. So this would be the equation of the tangent line. Okay, so if you're asked to get the equation, you go through, get the slope, but then you've got to go this step in order to get your equation. All right, what we're going to look at next is some situations in which a function is not differentiable, meaning that you cannot find its derivative. So a function is not differentiable at x equals c if the function has one of these three conditions. First condition is that the function is not continuous at x equals c. So if they're wanting to know, exactly at x equals 5, if it's not continuous at 5, therefore it's not differentiable. If it has a sharp turn at x equals c, or last, if it has a vertical tangent line at x equals c. All right, so what I have next is actually examples of each of these three situations. So the first situation was the graph was not continuous. And when you're putting these in your notes, you actually could just do rough sketches of these. You wouldn't have to get quite as detailed as what the graphs are here. This first one, this is actually what's called your greatest integer function, sometimes referred to as your step function because it looks like stair steps. But this would be a situation in which there are places that it's not differentiable. Now there are places that it is, but there are places that it's not. So if you were specifically looking at x equal 2, is it differentiable at x equal 2? No, it's not. Because right here, you've got, the separation in the graph there, or the jump or gap that's in the graph that keeps it from being continuous at x equal 2. It's not continuous at x equal 1 for the same reason, or at 0, or at -1, or at -2. Now, this is the only part of this graph that you're seeing, but these stair steps would actually just continue in both directions. So since there's several places it's not differentiable, I've just kind of written it in general terms here. I said it's not differentiable at x equal n, where n is an integer. So if you remember, 0, 1, 2, 3, 4, -1, -2, -3, those are all called your integers. So since I've said n represents an integer, it's at any of those values. Now, if you were asked, is it differentiable at x equal 1.5? Yes, it is. Because 1.5, see, would be right here, and it is continuous at that exact point. It's just at these integer values in which it's not differentiable. Okay, the second situation referred to not being differentiable at a sharp turn. So that's what we have at x equal 2. Of course, this is your absolute value graph, but that would be a sharp turn. So anytime it comes to a sharp point, of course it refers to it as a sharp turn, then it's not differentiable at that point. So I'm not saying the whole function is not differentiable, it's just not at that point. So like if I ask you about x equal 3, yes, at x equal 3 it's perfectly okay. You could find the derivative there. Okay, last situation was if you have a vertical tangent line. And that's kind of hard sometimes for you to understand, but exactly at x equals 0 is where you'd have to have a vertical tangent line. So like if I drew my tangent line in, so it would have to be right here, because that's the only way that I could draw a tangent line that touches this graph at just that particular point would be there. I couldn't draw it any other way. If it's tilted just the slightest bit one way or the other, then it would actually end up touching your graph here and here if it tilted just a little bit, like I said, one way or the other. So it would have to be perfectly vertical in order for you to have that vertical tangent line. Again, it's differentiable everywhere else, just not at x equals 0.